Hi, in this video you will learn to significantly improve the running time of the Rabin-Karp's algorithm. And to do so we will need to look closer into the polynomial hashing and its properties. Recall that to compute a polynomial hash on a string S, we first choose a big prime number for the polynomial family, then we choose a random integer x from 1 to p-1 to select a random hash function from the family, and then the value of the hash function is the polynomial of x with coefficients which are characters of the string S. And to compute this hash function on a substring of a text t, starting in position I and having the same length as the pattern for which we are looking in the text, we need to also compute a similar polynomial sum. It goes from character number I to character number I plus length of the pattern minus 1, and we need to multiply each character by the corresponding power of x. For example, t of I will be multiplied by x to the power of 0, because this is the first character of the substring, and the last character will be multiplied by x to the power of length of the pattern minus 1. And here is a formula on the slide. And the idea for the improving of the running time is that the polynomial hash value for two consecutive substrings of text with length equal to the length of the pattern are very similar, and one of them can be computed given the another one in constant time. We introduce a new notation. We denote by big H of I the hash value for the substring of the text starting in the position I and having the same length as the pattern. Now let's look at the example. Our text is ABCBD, and we need to convert the characters to their integer codes. And let's assume for simplicity that the code for A is 0, for B is 1, for C is 2, and for D is 3. Then our text is actually 0, 1, 2, 1, 3. Also, we will assume in this example that the length of the pattern is 3. We don't need to know the pattern itself, we just fix its length. So we will need to compute hash values for the substrings of the text of length 3. There are 3 of them: ABC, BCB, and CBD. We start with the last one, CBD. To compute its hash value, we first need to write down the powers of x under the corresponding characters of the text. Then we need to multiply each power of the x by the corresponding integer code of the character, and we get 2x and 3x squared. Then we need to sum them, and we also need to take the value modulo p, but on this slide we will just ignore modulo p, it will be assumed in each expression. Now let's look at the hash value for the previous substring of length 3, which is BCB. We again need to write down the powers of x under the corresponding integer codes of the characters. We again need to multiply the powers of x by the corresponding integer codes and get 1, 2x, and x squared. We need to sum them. Now note the similarity between the hash value for the last substring of length 3 and the previous substring of the length 3. To get the last two terms for BCB, we can multiply the first two terms for CBD by x. And we will use this similarity to compute the hash for BCB given the hash for CBD. So again, big H of 2 is the same as hash value of CBD, because it starts in the character with index 2, and it's equal to 2 plus x plus 3x squared. Now let's compute big H of 1 based on that. It's the hash value of BCB, and we know it's equal to 1 plus 2x plus x squared, modulo p. Now let's rewrite this using this property of multiplication by x, the terms for the CBD. So it's equal to 1 plus x multiplied by the first two terms for CBD, which are 2 plus x. Now we don't want to use just the first two terms for CBD, we want to use the whole CBD. So we write this as following: 1 plus x multiplied by the whole expression for CBD. But now we need to subtract something to make the equality true. And that something is the last term, x multiplied by 3x squared, which is the same as 3x cubed. So we subtract 3x cubed. Now we regroup the summands and we write as this is equal to x multiplied by the hash value for CBD, which is big H of 2. And we add 1 to it, and we subtract 3x cubed. In the general case, there is a very similar formula. So here is the expression for big H of I plus 1. And notice that the powers of x are, in each case, j minus I minus 1, because the substring starts in position I plus 1, so we subtract I plus 1 from each j in the sum. And the expression for big H of I is very similar, but for each power of x we subtract just I from j because the substring starts in position I. Now let's rewrite this expression so that it is more similar to big H of I plus 1. And to do that, we start summation not from I but from I plus 1, and we also end it one position later. So the first sum is now very similar to the expression for H of I plus 1. Just the powers of x are always bigger by 1. And also we need to add t of I, which is not accounted for in this sum, and we need to subtract its last term because it's not in the expression for big H of I. And that is t of I plus length of the pattern multiplied by x to the power of length of the pattern. Now notice that the first sum is the same as x multiplied by the value of hash function for the next substring, big H of I plus 1. And the second and third terms are the same. So now we get this recurrent formula. To compute big H of I, if we know already big H of I plus 1, we need to multiply it by x and then add t of I and subtract another term. Notice that t of I and t of I plus length of the pattern we just know, and x to the length of the pattern is a multiplier that we can pre-compute and use for each I. Now let's use this in the pseudocode. Here's the function to pre-compute all the hash values of our polynomial hash function on the substrings of the text t with the length equal to the length of the pattern and with prime number p and selected integer x. We initialize our answer, big H, as an array of length of text minus length of pattern plus 1, which is the number of substrings of the text with length equal to the length of the pattern. Also initialize s by the last substring of the text with the length equal to the length of the pattern. And we compute the hash value for this last substring directly by calling our implementation of polynomial hash with this substring, prime number p, and integer x. Then we also need to pre-compute the value of x to the power of length of the pattern and store it in the variable y. To do that, we initialize it with 1 and then multiply it length of p times by x and take this modulo p. And then the main for loop, the second for loop, goes from right to left and computes the hash values for all the substrings of the text, but for the last one for which we already know the answer. So to compute h of I given h of I plus 1, we multiply it by x, then we add t of I and we subtract y, which is x to the power of length of p, by t of I plus length of the pattern. And we take the expression modulo p. And in the end we just return the array with the pre-computed values. So to analyze its running time, we know that initialization of array h of s and the computation of the hash value of the last substring all take time proportional to the length of the pattern. Also, pre-computation of the x to the power of length of p takes time proportional to the length of the pattern. And the second for loop takes time proportional to length of the text minus length of the pattern. And all in all, it's big O of length of the text plus length of the pattern. Now again, polynomial hash is computed in time proportional to the length of the pattern. First for loop computing the power of x also, and the second for loop, which goes through all the substrings of the text with length equal to the length of the pattern, takes length of text minus length of pattern time. And the total pre-computation time is proportional to the sum of length of the text and the pattern. And in the next video, we'll use these pre-computed values to actually improve the running time of the Rabin-Karp's algorithm.